So you studied about Monte Carlo, right? So you know Monte Carlo is an episodic paradigm of solving the reinforcement learning problem, right? TD learning is the continuous version of that, okay? There is a distinction here that or rather a point that I wanted to mention here, MC and TD. TD, both of these, what do? They work on policy evaluation, right? We just get the value functions, the v pi's, okay, which eventually converge to v primes, v stars, which is the optimal value function, okay, the ground truth basically of that state. However, our policy that we get, right, the policy that we derive will have to have the actions, right, because policy is what? Set of actions series together, okay? So we need Q for that, right, which is the action value function, okay? For that, we have to go one step further and use these algorithms, the TD algorithms or the Monte Carlos, whatever we have, to then improve the policy rather, right? You remember there were two steps in policy iteration, right? Policy evaluation and policy improvement, right? So this point was done. So now the other step was policy improvement. So for this we use two methods, SARSA or Q-learning, okay? Both are same in the sense that both try to obtain or let us get the optimal policy, okay? However, the difference lies in the way of we obtain the optimal policy, okay? Now, we were talking about on policy and off policy. Okay, I'll talk about that later. So just to give you an overview, again, Monte Carlo and TD are model-free methods as opposed to DP, dynamic programming, use the model. So here we don't have the model, okay? Monte Carlo, the entire episode, because we use the actual returns, whereas temporal difference or TD learning, it can be parts of the episode, okay? Depending on your lambda that you have or n, right? This, if you have 0, it means it's one step. If this lambda tends to infinity or end of episodes, this will simply become Monte Carlo, right? Or if you have an intermediate number n here, then it will balance between these two, right? Balance in the sense, what are the terms or factors that we are trying to balance? There is something high, something low. You remember I used the term, this is high and this is low. Recall, guys. No, but something related to learning. Variance, right. The variance and bias, right? There's a trade-off between these two, right? For Monte Carlo, what was high, what was low? Variance is high, yes, and bias is low. Why? The episodic change is significant. That's why the variance is higher. However, because it is using the real estimates, the difference from the mean actual true value is small. For the bias is small. Clear? Clear? Okay. So we have that done. Okay. So we then talked about bootstrapping, right? What was bootstrapping? The idea of bootstrapping simply states that if you're using an estimate to again estimate something else, therefore when there are two estimates involved on both sides of your equation, then you are bootstrapping something, estimating something, right? Okay. In Monte Carlo, we use the entire episodic return, GT. There is no estimation involved there. However, in this one, because we take only one step forward and then we rely on the estimates of the return, which is nothing but the expected value function, the Bellman expectation equation. This is an estimate now because we are using an expectation here, right? So TD learning will have this expectation function instead of the actual returns. Okay?
Yeah, but you said an estimate of an estimate.
Yes, value function initial, okay. The value function, the target that you have is again estimate. Remember when we talked about delta here, when we talked about delta, it was R plus gamma Vs minus Vs. Sorry, this is S dash and T plus 1, right? S. So this is the target that we want to reach to, which is again an estimate because this itself is changing. You remember I told that the target or the target that we have keeps on changing as we move further in the episode or further in the training process, right? Okay, because we don't know, we don't have the model of the system, right? We don't know the actual value functions of any state, right? So we are simply blindly starting, and as we go further, we are like, okay, assume you are driving somewhere, okay? You don't know how far that is. You keep estimating the distance. You're like, okay, probably somebody might have told you that, okay, it is very far. You just assume that, okay, very far simply means 50 kilometers. But as you go further and further, say you reach 40 kilometers and you see outside, you have a very strong binoculars, okay, and you can see 10 kilometers ahead. You see that there is no city there. You're like, oh no, my initial estimate of 50 was wrong. So my target is now changed. So it's 100 maybe. And again, when you get closer to 100, you realize, no, it's not 100 again. Again, you go further. Again, you go further. So your target itself is an estimate there. And then you're estimating the actual value function based on that estimate, right? Yes.
The Monte Carlo has high variance with low noise, right?
Low bias, yes.
Okay, how about the other one?
No, not noise, it's bias, okay.
Low bias. How about the other one?
Other one has lower variance but higher bias, okay? Because we are using estimates there, so there will be a lot of difference from the true value. But because it is estimates and we are doing it in, what do you say, for every step basically in TD0, the change in that value function will be smaller, right?
So low variance and high bias.
High bias, yes. And also, okay, here we are using something called, okay, this update method, okay, where new estimate is equal to old estimate plus the learning rate times the target minus the old estimate is nothing but stochastic gradient descent. It's SGD, right? Any standard SGD update is based on this principle. So we are simply using that principle here. There is no new derivation or new math here, right? This equation is obtained based on... Exactly. Exactly. No, yes, for reinforcement learning, it is in fact back propagation in a sense. You will see when we go to deep learning methods, deep reinforcement learning methods, that this is that in fact. Okay, so there is back propagation in this one. So we are just trying to upgrade or update the values that we have based on some new estimates that we are getting. So we are applying stochastic gradient descent here. Okay, so yes.
Where are we doing the gradients here? I don't see that.
You mean here?
Like, why that gradient descent in the first place?
Okay. We have value function as the expectation of the returns. Here, your expectation returns can be written as the current reward plus the future expected value functions of that state given is. Okay. Now, okay. See, this is an estimate. You make this estimate, okay? You could do for the entire episode if you have model of the system, okay? Since you don't have the model of the system and you're doing it only one step, this simply becomes, for one step, this simply becomes R plus times V pi, V pi of S prime, T plus 1. So basically we are doing one sample only. We don't care about the remaining world. If there is a grid world, we just take one step forward, we consider only that one step, and because we don't have the model of the system, nor are we waiting for the entire episode to complete, we will rely only on this one sample. This is called a sample. This single entity, okay? Now, okay, I'll skip the math here, but if you do the derivation and if you apply the stochastic gradient descent algorithm here, you will reach to this this equation. That's why I have written it somewhere here, probably in the next slide, yes, that this is simply from SGD. Okay, I can forward that derivation to you probably. If I'll share that derivation with you. That will help you better, I'm assuming. Okay. Is again like it's also from the first order difference equation where delta is the old estimate, no, new estimate minus the old estimate. Okay. So based on this we'll solve a numerical as well now because we already did this earlier.
So are you saying that back up?
Mm-hmm.
So are you saying that this is basically the gradient? It's just we are discretizing it, so it's a difference equation instead?
Yes. Because it's remember we are applying this for a discrete world now. So therefore everything is discretized here. The differential will become the difference here. Derivative will become the difference here. I'll do an example directly for SARSA because for TD, we could do one for TD as well, okay? This is, okay. Say your current estimate of the present state is 5, okay? That's why VS is 5. And again, your current estimate of the next state is 7. The reward that you're getting is 1 with a discount factor and learning rate of the given value, the given values. So now your updated state estimate of that state is 5.23, right? So now you see, did we compute the entire returns for all the episodes? You remember there we had to add a trajectory like A, B, C, E, T or whatever in Monte Carlo, but here you don't need that, right? Here you simply can do one step and you get the updates, right? DP was an exact method because you have the model. Here you are simply sampling and based on that sampling you're updating your value functions. So it is an approximation method for what DP is doing. Basically the job of TD and DP are same, it's just the way they are doing is different because of the availability of resources. Okay? Yes, this I explained here already. You can have multi-step TD, and when the number of steps tend to infinity, you will get Monte Carlo. Anything in between, you balance variance and trade-off accordingly. Okay. What did we see from this from the example that we had? That every step, the values are being updated. Therefore, it's online learning in that sense. We are not waiting for the entire episode and then updating it based on what we saw. We are doing it on the go. Hence, it's online learning. Okay? And then we have another classification. In the next lecture, we will talk about the taxonomy of the RL algorithms as well. That will give you more clarity. We already talked about this in the previous class. Basically, it states that yes, there are theoretical guarantees that your value function approximation will tend to the ground truth or the optimal value with 100% probability of 1, that is. Okay? Okay. On policy and off policy, right? We spent a bit of time in this in the previous lecture as well. Just to again give you a brief overview. On policy is something that if you're following a given policy and you're improving that. So if I write it, I will write something like this. You're following the policy pi and then you're getting the V pi, okay? V pi for that policy, okay? You update this policy or you update this value function, okay? This is on policy, sorry. However, if you have V star and you have V pi, or rather you have policy pi and pi star, you are following this policy. What do you mean by following policy? What is policy? Set of actions. So if you are following, say, this action, this policy has a set of actions given here, okay? Using these actions, you are updating this policy, then it is off policy. Okay. An example I came across was this. So say there are two footballers, okay? They're training, both of them are learning. They are on ground, they're learning. Both of them have, the coach is recording the videos for both of them, okay? One, what he does is, assume player A plays the game, okay? Takes the recording, goes back with the coach, then he's like, see, at this point, you shouldn't have passed the ball like this. So next time when you're in this situation, that is, say maybe you're surrounded by the defenders here and your teammate is there, pass the ball at this angle, at this velocity to him. Okay? However, this is on policy because he is trying to correct the actions taken by that very own player. Right? Now, off policy means he records the video, okay, of that junior or amateur footballer, and then he has the video recording of, say, a professional footballer, a pro footballer, okay? And then he's like, see, at this point, this pro player will take this action. So you should try to do that, right? That is the best case scenario, right? So you see that both of them will eventually learn football equally good, probably. Well, here the assumption is they will learn football equally, okay? They will both be equally good players. However, you see the way this is learning, like here you already have an optimal policy, okay? Based on, yes, okay, assume you have a very good policy there and you're trying to mimic that policy. Or rather, not mimic policy. You're trying to learn the policy from that thing, from the pro player, okay? Which obviously would, if you're trying to do that, you will do it quicker, right? Because you already have a template, a very good player. You're like, okay, fine, he does the pass this way. I will do that. That's it, right? If you're gradually improving your policy, you will reach that level of proficiency, obviously, but it will take you a longer time. Longer time as in more samples. You go to the training, you do the passing again with your teammates, you're like, oh, again, no, okay, this I have to improve. I improved this part, probably the angle was good, but the velocity was not good. That's why the opponent player was able to cut off the pass, right? Something like this. You get the idea now, right, of on policy and off policy? Okay. Okay. So here we talked about this thing, right? So TD was policy evaluation. Now we want to improve on that policy or simply extract the optimal policy. So we need some other methods. For that, you have SARSA, the on policy method of TD learning. Okay? Okay, yes. The name comes from state, action, reward, state, next action. Right? SARSA, the acronym for that. On policy in general takes more samples, yes. Okay.
No, hold on. SARSA is off policy.
SARSA is on policy. SARSA is on policy.
But isn't off policy more samples?
No, off policy is more policy efficient.
Why is that?
Just because of, okay, here you're trying to improve the policy, that is, you take this, okay, like the footballer thing. You basically say, the coach tells you, improve the angle and velocity of your pass. The next training, however, you're not able to improve the velocity. You're simply able to improve the angle of the pass. But again, you'll have to redo it, right? So now you see, okay, the angle was good. I did not. So you will then inspect as to why you were not able to generate that velocity on the ball. Like, okay, fine, I have to do this again now to improve the velocity at this passing angle. So you see, just to improve angle and velocity, you're taking 2-3 steps. And even then, when you reach that point, you will then realize, oh, that might not be a good thing. There is still room for improvement.
But wouldn't it make sense, like, doesn't it make sense that if I'm learning from a different policy, it would be more steps maybe?
No. It's not learning from different policy, it is improving a different policy. In the sense that you take an action, okay, when I do the example, it will be more clear how we are using, so here okay, from the equations, for SARSA equation, the equation will be something like this, RT plus 1 plus gamma times Q of pi times S comma A. Okay, however, this is for SARSA. However, we have RT plus 1 plus gamma times max over the actions of Q pi S comma A. This is Q learning, off policy. This is on policy. So here you see that we are not using the best action. Here we are assuming that even during exploration, if we take an action which is not good, we still compute the value of that state action pair based on the maximum value that we get, right? If I do, I'll explain it in the numerical question. I have both. We'll try to do them quickly. Okay. So yes, the SARSA update rule involves, like you see here, like again, it's the same thing. This doesn't change. Simply from V to Q, right? In TT learning, you had V because you were evaluating the policy there to obtain the optimal action state value functions. Here, you're doing the same thing, but for state action value function, right, or the Q function. Okay. Again, because there is no inherent exploration in this, we try to instill some kind of exploration into it by using the epsilon greedy method, which states that simply define a threshold epsilon, okay, between 0 and 1, and if the number is, say, less than epsilon, take an exploratory action. If the number is more than epsilon, take a exploitation action, that is, take the greedy action, the maximum action that you can get, hence epsilon greedy, right? Clear on this? Again, the convergence properties of SARSA are similar to TD learning in the sense that yes, here the optimality is guaranteed, that is, you will reach the optimal Q value, which in turn would give you the optimal policy. Here you have an environment which states A, B, and T. T is terminal. Okay. You have only two actions, left and right. This is states, this is actions. Okay. Okay. This is not a good one. Okay. The reward transition is something like this. If you go from A to B, you get a reward of 0. Okay. And that is through the right action. If you take a left action in A, you will go in A, but because you are hitting a wall, you get a minus 0.2. Okay. Then from B again, you take an R, you take right, you go to the goal for which you get plus 2. However, if you take left in B, you will go to, oh, this is plus 1, sorry, right. Plus 1, this is minus 2. And you go to A. Okay, this is the, just for one, because this is not the model of the system, mind you, right? Because this is only for one pair of actions that you have, right? From A to B and terminal, okay? And this is just to explain you the concepts. Hyperparameters, alpha, gamma, and epsilon, which are the learning rates, discount rate, and the epsilon greedy term for exploration are as given here, okay? You need to first initialize. So Q here is 0, 0, 0, all zeros, basically empty, right? Q for, so basically it means Q state is A, action is R, this is 0, QAL is 0, QBR is 0, QBL is 0. Okay? This is just the initialization, right? Now, learn Q to get the optimal policy using SARSA updates. Yeah, okay, I have it here. Okay. Your initial estimate is 0, right? Now say you are in A and you take a right action, randomly, right action, right? Because there is no model here or anything, so we simply assume that we take a right action. What's the reward, immediate reward that you're getting if you take a right action from A to B? 0. Okay, first I'll write down the formula. Keep this in mind. Your updated Q value estimate is plus alpha times delta, where your delta here is R plus gamma times VST plus 1 minus, oh, Q, sorry. Q minus QS. It's not here. Okay? Right? These are your formulas. Okay?
So this is temporal difference, right?
This is SARSA. We are directly working on Q now. We are not estimating V. You simply replace these values by V here. You will get the TD part, just the policy evaluation part. But our goal is to directly obtain the optimal policy, which is policy improvement. Right? Okay. So, so first one, QAR. Okay, we are trying to now obtain the value of QAR. What is this? Initial value of, sorry, this is A. Everything is comma A here, remember. Okay. So, how does it go here? First, let's calculate this. R equal to 0 plus, no, it's 1. 1 times 0 minus, because initialization is 0. For now, we don't know. So what will your QB, comma, whatever, 0. Okay. So this totally becomes 0. So this term now is 0 plus alpha is 0.5 times 0, which is 0. So your QAR is 0 at this point. Okay. Then what you do is, you assume you're at B. Okay. Now you're at B, and because you're not going there and then trying to estimate that. You're again, or compute that. You're just trying to estimate based on where you are. Okay. If you're at B now and you take a right, so now QBR. Let's assume this one. Okay. So first, this was, so delta 2 now, reward. If you take right, what reward are you getting from B? Plus 1. Plus gamma is 1.0. Your, if you, okay, of this one, QBR, initial estimate was 0. Because the, sorry, yes, if you take a right, you will end up in T, which is again 0, right?
This part we take the initial estimates, right?
Initial
That's
estimates.
what you're doing, so you're not taking the update.
Yes. Right, in the next step, you will take the updated one. Because this is online, remember, right? You remember online, offline? If you are waiting for the entire episode to then use the updated values, it's offline. If you're doing it on the go, it's online. Okay? Minus Q of B comma R. What was B comma R? Initial estimate, 0. So your final delta is 1, right? Delta 2, I mean. Now you have, okay. So now your QBR would simply be 0 plus alpha is 0.5 times 1. So now your updated QBR is clear up until this point? Are you sure?
Can I ask you a question?
Yes.
What we are going to do, like last time you said we were going to do an example on TD. We were waiting whole bunch to do an example on TD.
Oh, it was SARSA. I wanted to do directly SARSA. That's why I skipped this SARSA TD example. You want me to do?
Struggling with the TD concepts, and you said we were going to do an example.
Okay, I will do that example as well. It's exactly the same principle. Okay, instead of Q's here, you will have V. Okay, and you will not have 2 for every state because V is a function of S only. So it will be VS, sorry, V of A, V of B. Initially it will be 0 again. Okay, I'll do it now. Say V of A, 0. V of B, 0. So if you are in A now, your delta would be what? 0 plus, what's that? Where is that? Okay. Gamma is irrespective of gamma because your V of S plus 1, that is V from A to B is 0. So this difference is 0. So your updated value, your VS alpha plus delta, since this term is 0, your VS remains constant. That is, your VA would be 0 after the first iteration. Okay? Now go to VB. Your delta would be now what? Plus 1. This is assuming you take a right action, plus alpha is gamma, sorry, yes, gamma is 1. 1 times 0. Okay, so this would be 1. Your delta here now is 1. Okay, this was delta 1, this was delta 2, this was delta 2. So your VB now would be 0 plus 0.5 times 1, 0.5. Okay?
SARSA is TD, but in terms of Q?
TD in terms of Q, because we are trying, okay. From this, we are trying to obtain the optimal, you remember when we were doing dynamic programming, what did we do? We have two methods there, value iteration, policy iteration. Value iteration, you could directly get the optimal policy without evaluating the policy because you're doing max over the actions right away. In this one, in policy iteration, you had two steps, policy evaluation, policy improvement, right? So TD learning is basically policy evaluation part of that, and SARSA is the policy improvement part of that. That's why we are doing it over Q now. You repeat this over many episodes. Now next time when you start, you're like, okay, fine, I use these values. If you have say 3 or 4 states, A, B, C, you can use the updated value right away, right? However, because there are only 2 states here, you get 2 values. Next iteration you do, start with 0 and 0.5. Repeat the same process. Again, update your values. You get second VA and VB after second episode or second iteration. Again, use that values, do it again. So basically, a iteration till, when do you stop? Sorry? Exactly. Or very small error. If the difference between any 2 consecutive iterations, the difference in the value function of any 2 iteration is below a certain threshold, ideally 0, you will stop because then you have converged to the true value or optimal value, right? That is the TD learning part. Yes.
So how did we know that Q of S plus T plus 1 is equal to 0?
Where is that, by the way?
And delta evaluation.
Okay, I'll rub this, I'll come to that. You mean for the SARSA part, right?
Yes.
Okay. Do you know numerical approximation methods like Newton-Raphson method or Euler methods? Okay. What do you do in that? You start with an initial guess, estimate, and then you iterate over it. Again and again and again and again till the delta becomes smaller than a threshold. Even here exactly, you initialize everything as say 0. You can initialize anything for that matter, okay? You don't have to keep it 0. You can keep it 100 maybe, for example. Okay? But you don't do it. Why don't you initialize with say 100 or 1000 or million?
Using large numbers, one complicates the numerical aspect. Also, if we start with, let's say, a large positive number and our actual value is negative, then we would have to come along and vice versa.
Exactly.
So we start in the middle and wherever it goes, it goes.
Exactly. Even if you know for certainty that your values would be positive, you still tend to start with 0, like say in case of neural networks, where you initialize all the weights of the neural networks, the weights and biases, to a very small number. Why? Because the calculations shouldn't explode, right, if you use larger numbers. This is just general AI theory. Like even in neural networks, you tend to start with smaller initializations. Okay. Anyways, back to this one. So you start this initialization. Okay. Now I'll write this a bit clearly so that I can explain you. Here you have R plus gamma of, gamma of Q S t plus 1 comma A t plus 1. Okay. Minus Q of S t comma A t. Okay. So now you're asking me, how did I get this value as 0?
Exactly. Because we
From here.
initialized the second term, right? The first one.
Sorry?
The initialization there
Uh-huh.
was for the second term, which is QSTAT.
Okay.
How did we get the first one?
What is your ST plus 1 and AT plus 1 here? Assuming you start in A, what will be your ST plus 1? What will be your next state? So we have the initializations. Without that, we cannot start, right? Because this is a numerical method and not an analytical method where you have equations, but then you don't have, like, you have to have some kind of guess, right? All numerical solutions, you need some kind of guess to start it with, and that is our guess basically.
We're applying policy iteration, right? With policy evaluation and policy improvement.
Yes. Well, it's not exactly policy improvement and policy iteration, but I just wanted to use that as an example here to explain that TD was just the evaluation part, now we are doing the improvement part. Right? Up until this point, what did we do? We just evaluated the value functions. But simply knowing the value functions will not tell us what to do, right? We simply know that the states are good, 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 good. But how do you go to that good states? That will be through the policy. And for policy, we need Q. Okay? Now, when you're doing the second episode, you remember this SARSA follows what exploration strategy? Epsilon greedy. Epsilon greedy was the SARSA's exploration policy, method, right? Otherwise, SARSA would be stuck in a loop where you simply just take the max actions, you don't explore the world enough, you will never know if there is a better path or not. Okay? Clear, everyone? Okay. I will do it here. So now again you are in state A. Okay? You take a right now. Okay? And at B you have two. Okay. Okay, yes. Again, step 2 now. Or rather episode 2. Okay, episode 2, the second iteration, that is. You start with these initial values. Okay? You have certain epsilon. Okay? Assume your epsilon gives you a value where you have to exploit now. Okay, assume you are exploiting. So here, since both actions, right and left, give you the same thing, we simply set a rule that if it's a tie, we take right. Okay? So now you're taking right in A. Okay? Where are you ending up? A right will end up in B. B right will end up in T, the terminal condition. Okay? So what you are doing now is A right, okay, B right had its value updated 0.5. So now QAR, again delta 4. Delta 4 would be reward immediate 0 plus gamma is 1 times, now it is 0.5, it is not 0 anymore, right? Minus old estimate 0, so this is 0.5. So now QAR, okay, QAR would be old estimate plus alpha is half times half, 0.25, value updated. Okay? You do this again now for, you're now in B, okay? And again, B, which action should you take, right or left? Because you're following epsilon greedy, we are simply following the policy where we exploit now. So which action should you take? Right. So that would again give you your delta 5 now, right? Delta 5 would be, if you take a right, you get plus 1 plus, your next state is nothing, so 0. So this is 1. So your QBR updated would be old one plus learning rate times new one, right? It would be 0.5 plus 0.5, 1. So your QBR is 1 now, after the second iteration. Okay? Clear up until this point? Yes. For the first one, 0.5 here, you mean? This one? Okay. What is this delta? This delta is reward plus discounted value of the future state where you end up in. So from A, if you take a right, you will end up in B. So B, 0.5. Okay. We did this computation, but again, since we are not doing the evaluation part here, what you can do is, you remember okay, we simply consider now this value and this value. Sorry, this value, right? Because this is policy improvement, right? You can take only one assumed action in the state, right? So assume our pi1 was right comma right, okay? Initial policy. This doesn't have to do with epsilon greedy, because initial policy is something that you set arbitrarily, okay? Yes, the policy we are on policy. Yes, so we are improving the policy that we are following. Okay, we are following the policy. Yes, this is initial guess. Okay, this is simply an initial guess. Right, comma right. It can be anything.
But shouldn't it be an optimal? Like when we were talking, we were saying it should be like an optimal policy that it follows and improves.
That is off policy. It's not optimal, by the way. It is improving a different policy. Where, okay, so what you do is, even if you take an action, okay, in off policy, even if you take an action from the instructed set of actions that you are supposed to take, what you do is, I took this action in this state, but the other action had a better value in this state, okay? So what you do is, you ignore this mistake, you keep the value of the higher value. Like, ideally I should have done that. So the value of this state action doesn't change because you made a mistake here. You're like, ideally, if I followed the ideal action here, I would get a higher value here, right? It should just be R and R, because you're following the policy that you're updating the policy that you're following. Clear? So after first iteration, you get this. Now in episode 3, okay, because you're still exploring, I will, okay. So at A again, your epsilon greedy tells you choose a right. So what is QAR now? QAR was 0 plus 1 times, okay. So assume now in B, you're going to take left turn. Because what is this? ST plus 1, AT plus 1, right? Why did we take right, B and right here? Okay, that it was based on your epsilon greedy term, epsilon term, right? Now assume in this third episode, your epsilon is such that it's encouraging you to explore rather than exploit. So your random, yes. Epsilon greedy is random, right? So you will be taking a left turn now in B, right? So what was the initialization of BL? 0. Minus 0.25. The old estimate of, this is delta 6, right? Yes, delta 6. Your old estimate of QAR was 0.25. Clear? So your delta now is minus 0.25. Clear? Yes.
For QB and
QB of R,
the change and having 1 plus 0.
right? Because what was your, what was this? What is the reward that you're getting? 1. But change was what?
C, right?
T.
0.
0.
What of the minus?
Oh, right, okay. This was delta minus of, what was this? Right. So minus 0.5, right? Okay, so yeah, you get minus 0.5 here. So your this term will be minus 0.5, correct? So this will be 0.75. Okay, thank you. Yes, 0.75. I forgot this term. Okay? So you get this value. Now, you get this value for delta 6, which is for QAR in the third epoch. Okay? So your updated QAR would be old value plus learning rate times new value. So this would be 1.25 minus 0.125. So now your value is 125. right? Right? So here you see, okay, no, not yet.
Why were you talking about B here?
Because we want the next state, right? Here we have the next state and action. So we have to know like what's the action value function of the next state we are going in.
So I'm in Q, I'm in A, and
A.
I'm taking a right.
Yes,
So I'm gonna be in B, right?
B, but in B your epsilon is such that it will let you explore. That is not take the ideal action. So you're taking left,
To the left, yeah.
which would end up you using this value. Clear up until this point, right?
As example,
Yes.
we should in step 3 we should have used the value of B left in step number 2 if we have calculated it right.
Again.
We are in step 3.
We are in episode 3, okay.
Step 3 and we should calculate the value of B QB left, right?
Yes.
Which you put as 0.
Oh, no, okay. Because till now we did not reach BL. So that's why we will use the previous estimate that we have. And our initial estimate was 0. Here, your QBL is still 0, so you're using this initialization. Now that you are in B and you're taking a left, you'll compute the value of QBL. Okay? Remember QAR is 125. Okay?
Next would be QBL, not QBR.
Yes, QBL. Because here what did we assume?
That our next state is
QBL. So we are updating based on that policy. Now the policy is what? Policy 3 is
right left.
right left. Okay? Clear on this? Yes.
Zero.
Sorry?
Zero.
First 0, second 0. It is your next state, next action. Initialization is at 0.
I mean, step 3 or step 2? Step 3 or step 2?
3. Because even in step 2, what was your policy? Okay, I'll write it here. Your pi 1 was right comma right. Your pi 2 was right comma right again. Your pi 3 is right comma left. Okay?
Why?
Random. You remember we used this epsilon greedy thing? This is anyways an initialized value that you simply start with, arbitrary, okay? But from here onwards, what you do is you use epsilon greedy, okay? Your epsilon was how much? 0.1, okay? So say you get a number, okay, epsilon. What does epsilon greedy theory itself or the epsilon greedy method? If you have epsilon and you basically roll a die. If you get a number less than epsilon, you will explore. If you get a number more than epsilon, you will exploit. Clear? Clear. So that's what you're doing here. Here we got the epsilon such that in both A and B we are supposed to exploit. So we are using the max actions. However, the next time when we do, we are getting exploit in A and explore in B. Okay? So basically based on this policy, your QAR has gone down. Right? So now QBL. Your delta. So reward, if you take a left, would be -2 plus your gamma is 1, okay? And you then end up in, based on the policy QAR, which we calculated as 0.125. This is on policy because you're using the updated policy right away, updated number. You're not using 0.25, right? Because in the previous episode, you got 0.25, but you're using 0.125. Why? Why? It's on policy. So basically you consider this value right away when you get it. Okay? So delta this minus 0. So this
Policy or online?
online. On policy is basically why we are choosing QAR here. Because we are updating the policy based on the actions that we take. Okay? So this number would be minus 1.8875. Okay. So now this was delta 7. So now QBL would be 0 plus 0.5 times minus 1.875, which would be minus 0.9375. Okay?
Doctor, why here? Like last week, we were saying that we use the values from the previous sweep or the previous iteration.
Because those values were updated.
Yes, I'm okay on the, like, for example, on 1 or 2. I mean, in iteration 1 or iteration 2, we use the values of iteration 1, right?
Where did this one you mean?
For example, I mean, I was asking about, we don't know, like, what we did exactly here. In
Okay.
the iteration, we use the updated value of QAR.
Oh, there was no term here where we could use it that way. Your initial were that thing, right?
Okay.
After first episode, it was QAR was 0, QBR was 0.5.
Yes.
Okay? QAL and BL same 0, 0 because we did not touch that because it was not a part of our policy. Second episode, QAR was 0.25, QBR was 0.75.
I mean, we didn't use the same QAR and QBR because QBR is terminal. We didn't use in the same iteration. We didn't use the same value of QAR.
We did. We did. But here, if you take a right,
Anyway, it wasn't A. The next
That's why.
action, it was terminal.
that's why if you take a right in B, you will not go to A. That's why we did not have to use the values of QAR.
So if I can use it, I'll use
Obviously,
the latest value.
absolutely. You use it right away in that iteration, as you're doing it here. You get the updated value, you plug it right away. You don't wait for the next epoch or next iteration. Right? Yes.
So basically, we start calculating the Q values from the start point.
From the start. Yes, from the start point, only for the next step. That's it.
Or we should look at the policy and see which will be the first state that we need to start with.
You could do it for any state that matter because what are you doing? You're just considering the reward. It's not the expectation for the entire series, right? It's just the reward that you're getting for that transition plus the discounted state action value function of the next state action pair you will end up in. Right? So it can be any two random states, provided you know this. Or if you don't know,
It should be calculated in case you need it.
you initialize. You initialize basically. So you can use that initialized value. Clear? Clear, everyone? Yes.
If we don't have epsilon greedy, and these values on the left won't be updated, right?
Okay.
Let's say if we have epsilon greedy of 0,
Okay.
right?
Okay.
So the values of the initial values of left, A left, B left.
Oh, so you mean okay? So you mean if we have epsilon as 0, you will simply exploit. That is, you will not change the policy, and you will exactly. That's the whole point of adding epsilon greedy term.
Yeah. What will happen? Let's say, for example, we have in this example we have left and right.
Yes.
Right?
Yes.
And what if we have a sort of action? If we have epsilon greedy, how it does work?
You take the third option, which is not the best one. Anything. You can take any of the remaining two options randomly.
Because for taking the equity, we need a random number, right? But after
Oh, okay.
this shows two decisions. We take the optimum decision or non-optimum decision.
Yes. So even in non-optimal, you have another 2 or 3 options. Maybe that's what you're saying.
We will have two options in,
Yes.
in the non-optimum. We run against epsilon.
Okay, that's an interesting, and thank you for bringing that up. Okay, I forgot to mention that. So what the assumption here is, how do you reach the optimal Q value function is by visiting the state action, every state action pair infinite times. So you basically repeat the episodes enough number of times till even the non-optimal options you have taken enough number of times, right? If you don't, now you get it. So you have to repeat the episodes as so many times that say, okay, in the first episode you have 2 non-optimal options and 1 optimal action, right? Your epsilon greedy now tells you to explore. So you have to choose one of these. You can choose any of those 2 non-optimal, because in the next episode you will choose this. Then again you will choose this. Then again you will choose this. You basically end up going in both states, or rather using both actions infinitely with that state. So you have to simply repeat that training till you cover that infinity times. You get me?
But we are not taking the optimal
Mhm.
action, right? We can take the maximum and the optimal action from this subset of actions. Let's say we have 2 more, we can take the maximum of this one.
Oh, so you mean a nested epsilon? So,
Yeah.
oh yes, okay. No, you simply take any random action that time. It's either optimal or not optimal, or rather maximum or not maximum. That's it. So any of those 2. But because the assumption, the underlying assumption is that you visit the state action pair infinity times, you don't care what you're taking, because you do it enough number of times so that you have covered everything, right? Okay. So now your updated Q values are, your QAR now is updated to 0.125, QBR is same 0.75, QAL is what? Oh, we didn't, okay, it is 0 because we did not explore it yet. And QBL is minus 0.9375. Okay. You see QR changed here, implying we still have to continue, right? None of the values QBR is same, but because we did not explore it. So basically, this is how you do the iterations, and you have to do it again and again and again till the Q values stop changing. Clear? Yes.
At the beginning, I responded to this question. We're into model 3, right?
Yes, model free.
How we know this?
How do we know what?
If you move right, you go from A to B.
You take that action and you then, based on the samples, you get this. You don't know you're going from A to B.
So this is assumed like to start solving, right?
Yes.
Okay.
You don't know you're going from A to
You
B.
don't start.
No, 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 no. You don't know. So you simply take an action, you end up going in B, and you get a reward 0. Then you're like, okay, I take this action, I will do this. Right? Clear? So this is model free. You don't have a model. You don't know that you will go from there to there. Okay? Also, if maybe there is stochasticity in the action, say you take the same action again, yes, exactly. You will maybe end up going in a different state. Yes.
I want to ensure from 2 points. When calculating QBL, the last one here, we use the next step as QA, right?
Right.
Because of epsilon.
No, not epsilon. We already using epsilon defined our policy. It's right comma left. Okay.
Right for A and left for
Yes. So when you are choosing QBL and your next action pair, state action pair would be left from B would end you up in A, but the action that you're taking depends on the policy that you have, the current policy, which says right. So it is QA based on this action, R based on the policy.
Okay.
Right?
We use the best value of QA right because this is on policy, right?
This is online learning, not on policy. This doesn't have to do with on policy. On policy has to do with this fact that we are choosing AR here and not AL. If it was off policy, here you could choose AL rather than AR. You get it? On policy implies that you are not using 0.25. What was the AR from the previous iteration? 0.25. In offline methods, what you do is and here you got the updated QAR, right? So if you were using off policy, you would have used this value. You would have 0.25 here, not 0.125. Because it is online, it means if you get an updated value, directly plug it in. You are using this updated value directly here.
So whether we are using on policy or off policy, as long as we are using online, we will use the best
Yes, yes, yes. Online offline has to do with the updated values. On policy of policy has to do with this policy. So now you get it, right? So if you are using QAR here, because you are using on policy updates. If you had chosen QAL despite the policy being right and left, it would mean it is off policy updates. Clear on this?
And that's like based on some policy we are following.
Basically it is based on this thing. So you basically choose max of QAL, comma QAR. That's what the equation is. Okay, that's what we wrote. R plus max over the actions of AST plus 1 comma AT plus 1. This was the target that we had, the Y of T.
That's off policy.
Off policy. We are choosing the max here. Hence, here we will not choose AR just because the policy says. We will compare or compute AR and AL and we'll choose the maximum value. Why? Why?
Because we are not, we're off policy.
We are off policy. So we are not restricted by the policy that we have. Rather, we are simply greedy to take the maximum value. Because we live in, say, a fantasy world where it tells us that even if for exploration you take a wrong action, this state is actually good because it has some goodness in it. So consider this while you're updating the value, not the wrong action, the bad action that you took in this state. Right? Clear on this? Yes.
If we are working on policy, we have to visit all states.
If you're working off policy, okay.
Take the maximum, right?
To take the maximum, yes, okay.
Yeah, I'm just confirming.
Mm-hmm.
Yeah, it's okay. Yeah, I understand.
Yes, so, yes, okay. So here, what did we choose here? QAR. When you took BL, you go in state A, right? A again have two options. You could either choose QAR or AL. But here we for sure choose AR. Why? Because our policy said that if you are in A, you have to take a right. So you have to, while computing the action value function of BL, you have to consider that you are going to take a right in A. So you will use that state action pair and you will use the value computed that. However, in on policy methods, which is Q learning, which we'll be doing in the next class, QAL or QAR, you compute both values and then you plug in the maximum value here.
That's off policy.
That is off policy. This, yes, that is off policy. This is on policy. Clear?
TD is on policy, right?
TD is neither. TD is just policy evaluation, like I said. That will give you V stars, not Q stars. This comes into play when you are policy improvement because you want to get the action, right? Clear? Okay. There's another interesting thing here now, okay? Again, here, when you take a right, okay, when you take a right in A, what value do you assume here? On policy. What do you assume here? BL, right? Why BL? Why not BR? No, here you took QBL. That's why you got 0 here. Why didn't you take QBR here? Exactly, because we are following the policy, right? Right? And you will see here that this reduced the value of QAR now. QAR was 0.25, QAR is 0.125, right? Same action in the same state will give you two different values now. Why? True value, yes, but then based on your BL, how did this AR reduce?
Because the current Q or the current quality depends on the future.
Exactly. So SARSA or on policy methods are conservative in this sense, right? Because a future effect is propagated here and you see the effect here already, okay? When we do the example for Q learning, you will see that this value will not change. You will simply get 0.25 again.
Because we just take the maximum.
We just take the maximum because we assume that We live in an ideal world where we'll always take the maximum action, irrespective what your policy tells you. Clear on this? Sure? So yes, okay. Next.